Now is the time. Now is the time to share an almost divine result with you. We're going to be quiet and pay due respect to this slide for a while. Read it, let it sink in, and get the feeling. If you want to cry, please do it. It's fair enough. You see something deep, it's allowed to cry. Yeah. I'm sorry if I get a bit emotional here, but let's try to dig into it. What are we here? This is the central limit theorem. I am now going one step further compared to my previous slides. I am not only thinking about whether my estimate on average hits the right thing, what is the precision of my average, of my sort of estimator, the average estimator, which is the variance. I'm also trying to speculate how is the distribution actually, and that is what we are going to know, become familiar with as the sampling distribution of the mean. What is the distribution? Is it a log normal? Is it a exponential? What the heck is the distribution? Because if I know the probability distribution, the probability sampling distribution of what I compute, in this case the mean, I know everything. I can be maximal intelligent about what can I use this average for, because I know its behavior in the future. Not only as one or two numbers, but as a probability distribution. That is the key issue, is in becoming intelligent about our numbers, knowing the sampling distribution. And here we have some theory that makes life easier for us. And the first part of it is here. Look at this. We take the average. I standardize the average in the way you worked around with standardization when you worked with normal distributions a couple of weeks ago for the first time. I subtract the truth. So basically, you could say the numerator here is the difference between my estimator and the truth, right? The difference between my estimator and the truth, that is the number I should be concerned about, right? Am I close to the truth or am I not? Then I standardize with, you could say, the square root of the variance. This is the thing I've showed you 2 times now on the slides before. I standardize by the standard deviation of this thing. So I have something, I call it Z, and here's the result. If we have something saying as n goes to infinity, that means if n is large enough, we could also say that is the same thing to say for large n. Large n in this course is beyond 30. It's not particularly large necessarily, but that's large enough. If n is large enough, then this statistic here, we could call it, that measures the difference between what I compute and what I want to know about, follows a standard normal distribution. Slam, here the result was. Let it sink in. I didn't claim any assumptions about, we had a population here, given by some distribution f, some density function f, that is a distribution of petrol usage here. I don't assume anything about this. It could be an exponential, it could be a normal, it could be, let's forget about the normal for a sec. It could be a uniform, it could be a bimodal, actually, it could be a very odd distribution. I don't fucking care in this result. No matter what the original distribution is, if I sample, if I take enough information, not only do I obtain higher precision with high n, I obtain a normal distribution for the sample means. So the normal distributions comes popping down from heaven here as a generic tool across everything, across all distributions out there in the world, to use for us to be intelligent. This is great. This is fantastic. Then there is a sub thing here that just saying, if the normal distribution already came in the same morning as the true model for the system at hand, then of course everything is normal from here off. I mean, if it's normal with n equal 1, then it's also normal no matter what the size of n will be. The big result is this one. Let us look at a couple of things I want to share with you. Not this one, this one. I want to just lead your attention to this plot in the book, showing how the central limit theorem works for something which could be, I think, it could be a log normal or it could be an exponential distribution. And here we have a uniform distribution. Instead of digging into this picture, I'm going to share with you some R stuff that illustrates the same picture. Here it comes. Some R stuff illustrating. Let's have a look at what I do now. Basically, I use the RUnif function, random uniform numbers. I take 1,000 of those. You don't have to follow the R syntax here. I'm telling you, I use the R uniform to make 1,000 such numbers that all come from a uniform distribution on the interval between 0 and 1. So it's random numbers between 0 and 1. And when I look at them, you can see they are uniform. I have more or less the same amount of numbers in the low end as I have in the high end, right? That's the uniform distribution. If I repeat it, I get the same picture, but of course slightly different, because you can see the histogram is changing just a little bit due to random variability of the uniform distribution. That is the starting distribution. What if this was the system that I was observing, something that came in as a uniform? What happens now? Let's have a look. Now I have a bit of technical thing here. What I do is that I now not simulate 1,000, I simulate 2,000, 2 by 1,000. And then I 1,000 times compute the mean of 2, right, of 2 of those uniforms. So I take like 2 rows of uniforms. So 1,000 times I have 2 uniforms. That's another way of saying it. I have those and I put them in a matrix, just like this. You can, not that we want to generally see it. What went wrong here? I think because I had caps on. So it's a 1,000 matrix of like 2 uniforms like that, right? Just to. Then I use this int-build function, apply. Again, the R syntax is not the important thing here, just if you are curious about it. You can easily apply those 1,000. You can easily compute those 1,000 means by this apply function. This is kind of a sweep function that runs through this matrix and computes all the means. So I have the apply. It gives me the 1,000 means. Now let me try to make a histogram of the 1,000 means. Whoa. You saw this? What happened? That's just because you're lucky, you say. Well, I'll do it again. Do it again. Here is how the means of 2 uniform behave. This is one step towards the normal assumption. What is going on here? Actually, it's a divine result, but it's a divine result that at least part of this divine result we can comprehend, I believe, we can understand. What is happening? Well, I simulate uniforms, and they are uniform. They come over the whole interval. Then, if I simulate repeatedly the mean of 2 uniforms, what happens with 2? Well, whenever you have 2, one will typically be a bit to the left, and the other one will be a bit to the right, more or less. It's quite unlikely, or at least a bit more unlikely, that both of them are very small, or both of them are very large within the interval. So typically they will be sort of scattered. They are scattered uniform. So when you average 2 of them, the average of 2 numbers is in between, towards the middle, right? So the averaging kind of operator, if you would call it that, from a math point of view, the averaging process takes things to the middle, moves things to the center, right? So the distribution of the means of two uniform is definitely not a uniform distribution anymore, right? So the means of two uniform does not have a uniform distribution, that's for sure. What is the distribution then? Yeah, that might be difficult. The exact distribution might be a bit difficult to find, at least in this course. If you're a probability guy, you could find it. But then we have our approximate result. Let's try it with taking the means of 6 observations. Just taking the means of 6 uniforms. We have something that I cannot see the difference between this and a normal distribution already here. And the rule is, as of 25 or 30, let's just stick to 30. Let's define 30 as being large. Whenever you have something 30, basically the result is indistinguishable. I mean, it's just some of the automized things. Sometimes it uses many classes, sometimes it doesn't use many classes. We can say that let's always use 15 classes here. We have something which is normally distributed now. This is a fantastic, great result. This is the central limit theorem. Before the break, I'd like to take you through the next. We make